Now we want to look at a theorem that relates determinant to invertible. So this theorem says a non-zero determinant means that the matrix is invertible. So I'm going to prove this theorem. This theorem has two directions, so we'll start with the forward direction. So if A is invertible, it must be row reducible to the identity. This is the invertible matrix theorem. And we're going to make a note that if the determinant of A is not 0, then the determinant of B is not 0 if B is a row equivalent matrix. And this just follows from the previous section where we looked at the effects of row operations on the determinant. So notice that none of these row operations can make the determinant 0. They either flip the sign, scale it, or leave it unchanged. So if the determinant of I is not 0, the determinant of I is 1, this implies the determinant of A is not 0. So that's the forward direction. Now we're going to go in the opposite direction. So if the determinant of A is not 0, A cannot be row equivalent to a matrix with zeros. And what I mean to say is row of zeros. Otherwise, it would have a 0 determinant. And because there's no row of zeros, there must be a pivot in every row. And if there's a pivot in every row, then A is row equivalent to the identity matrix. And by the invertible matrix theorem, it's thus invertible. Okay, so now we have another theorem that says the determinant of A equals the determinant of A transpose. We're not going to prove this in general, but we'll look at the proof of the 3×3 case. So let's say we have this A, which is A, B, C, D, E, F, G, H, I. And then we have A transpose, which is flipping the rows and the columns. Okay, so let's compute this determinant using the first row. So we'll do A times E, F, H, I minus B times D, F, G, I plus C times D, E, G, H. And this works out to be A times E, I minus H, F minus B times D, I minus G, F plus C, D, H minus G, E. So this is the formula for the 3×3 determinant if you wanted to memorize it. And now we're going to compute the determinant of A transpose. And instead of using the first row, we're going to use the first column, cofactor expansion. So this will be A times E, H, F, I minus B times D, G, F, I, and then plus C times D, G, E, H. And you can see this is going to work out to be the same thing. So these match. Okay, so our last theorem here is the determinant of a product. It says the determinant of a product is the product of the determinants provided both exist. And what I mean here is that both these matrices are square. Matrix needs to be square for the determinant to exist. Okay, let's look at an example. So let's say we have the determinant of A is 2 and the determinant of B is 6. Let's find the following determinants. Determinant of AB, determinant of A transpose B, and let's make this determinant of A transpose B squared, make this a little more interesting. And then the last one is the determinant of A inverse, assuming the inverse exists, which it does because the determinant's not zero. Okay, so using this theorem, determinant of A, B is the determinant of A times B, determinant of B, which is 2 times 6, which is 12. This one we have to do a little more factoring, so we're going to do the determinant of A transpose times the determinant of B squared, and then we're going to break that apart. The determinant of A is going to be the same as the determinant of A transpose, so I'll just replace this with the determinant of A, and the determinant of B squared is going to be the determinant of B times the determinant of B. So this is 2 times 6 times 6, so 2 times 36, which is 72. Now for this last problem here, we have to think a little bit about A inverse and how it relates to A. So I'll just remind you of the definition of A inverse. A inverse is the matrix where we multiply with A and we get the identity. Let's take the determinant of both sides. Determinant of the identity is 1. It's just the diagonal of 1s. It's a triangular matrix. It's a product of the main entries, main diagonal. And the determinant of A inverse A is going to be the determinant of A inverse times the determinant of A. These are both real numbers, so I can divide, and I get 1 over the determinant of A. So that's interesting. The determinant of A inverse is 1 over the determinant of A, and we're going to use this fact to find the determinant in this case, which is 1/2. So we have 1/2, 72, and 12. Okay, so let's look at another example. So let's say we have A is A, B, C, D, E, F, G, H, I. And let's say the determinant is 2. Let's find the determinant of A, B, C, G, H, I, 3D, 3E, 3F. Okay, so this is a modified matrix A. You can see that our rows are becoming columns, and we have some coefficients and some swapping. So what I'm going to do is we want to start with A and transform it to this new matrix and track what the changes are. And then we can track how the determinant's affected by those changes. So the first thing I want to do is swap the rows D, E, F, and G, H, I. That's one of the changes. And when we swap rows, the determinant gets a negative sign. All right, then we have the third row is going to get multiplied by 3. And we scale, the determinant's changed by that scaling factor. We multiply by 3. And then to get to this last form here, we're going to transpose. And when we transpose a matrix, its determinant is unchanged. So no change. Just write no change here. Okay, so we have 2 is going to get hit by -1. It's going to get hit by 3, and then it's going to be hit by no change. So that's going to be -6. But this was our b. Then determinant of b is -6.